all that material gets crushed down into a ball that is just neutrons.
In this video, I got the chance to talk to Dr. Andrew Cameron about pulsars and neutron stars. Dr. Andrew Cameron completed his PhD at the Max Planck Institute and is now working at the Swinburne University of Technology studying pulsars and general relativity. Now you might be thinking, how do pulsars form? Well, that's what Dr. Cameron will answer in today's video. Thank you so much for joining us, Andrew. I guess that moves on to our next question, which is how do pulsars actually form and how do they, start spinning and, producing these electromagnetic beams?
Well, the process of the formation is essentially in that core collapse supernova where you get the neutron star out the other end. The neutron star is the result of a supernova explosion where a star at the end of its life has fused heavier and heavier and heavier elements until eventually you get to an iron core. When that happens, the core of the star starts to collapse under its own weight. There's no fusion pressure. There's no energy pressure being produced by the interior to hold the whole thing up. So as the electrons and the protons get smushed together, all that empty space is essentially squeezed out, and all that material gets crushed down into a ball that is just neutrons. As to why they spin the way they do, that's essentially pure conservation of angular momentum. So every star, including our own sun, has some rate at which it is rotating. But because the star is very large, that rotation rate is typically reasonably slow. I haven't got the numbers in my head, but it's not super fast. But as that core of the star collapses down, by conservation of angular momentum, the rate of rotation speeds up considerably. So in the same way that if you're, say, on an ice rink and you're doing a spin and you've got your arms stretched out wide, if you drag your arms in towards you, your rate of rotation will spin up quite considerably. Or alternatively, if you're on some kind of merry-go-round ride at a playground and you hang out the side and you're going around and you bring yourself closer to the middle, as the concentration of material moves towards the center, it causes the rate of rotation to increase. So when neutron stars, pulsars, are born, they typically start out around spin periods of roughly 30 milliseconds or so, and then gradually slow down as they get towards the end of their lives over the course of some 100 million years or so. Now, as to why pulsars emit the way they do, that's actually a fairly complicated field of study. The short answer is that you've got the diagram of a pulsar on the right-hand side here with its strong magnetic field. That magnetic field is strong enough that it can cause charged particles to come off the surface of the neutron star and fill that magnetic field with essentially a dense plasma, the plasma being a medium of charged particles. And as those particles move along the magnetic field lines at both poles of the pulsar, their motion causes the emission of electromagnetic radiation. But it's obviously a lot more complicated than that. The model that we have on the right-hand side of this slide here is what we refer to as the toy model of the pulsar. It's only a very simplified diagram, and it assumes, a very simple magnetic field, what we call a dipolar magnetic field with a north and south pole. There are lots of models of pulsars that have much more complicated field structures than that. And I'll skip a few slides forward, in fact. There's actually a few more things I can show off here. So here you can see some of the pulsars that I've studied in the last few years. These were pulsars discovered by a telescope in China called FAST. It's the world's largest single-dish radio telescope. It's 0.5 kilometer wide. And you can see here, these are some of the pulses that we get from a handful of different pulsars as their emission beams cross the line of sight of the Earth. And you can see they vary in shape quite a lot. You've got single pulses, you've got double pulses, you've got like the one. So where my mouse is pointing here, you can see there's a pulsar that has a very complicated multi-peaked structure. There's one down here with 2 peaks, another one with 2 peaks. Some of them are fat, some of them are narrow. There are lots of different reasons why these pulsars could be producing pulses in the shape that they are. We have different ideas of which parts of the emission cone are turned on and turned off. People suggest maybe it's like a cone shape, or there's a core central portion which is turned on. Some other people suggest that the emission cone has patchy emission where it's sort of irregularly scattered, which parts are turned on and turned off. There are even some pulsars which tip over during the course of their lives. So, usually ones that are found in binary systems, as they interact with their binary companion due to the effects of things like relativity, the angle at which they're pointing at the Earth isn't constant. They will gradually tip over with time due to an effect called geodetic precession. So we can measure different parts of their pulse structure as they change their orientation, so we can map out the shape of the pulse over the course of the entire emission cone. So there's lots of different areas of active study going on, but a unified theory as to how and why pulsars emit the way they do isn't quite there yet.
Wow. So, any viewers who are particularly interested in doing a PhD in astronomy, call up Andrew. Links in the description.
Absolutely. There's still a lot of things about we've been studying pulsars for the last 55 years, but there's still a lot of things to work out.
Oh, wow. That's super fascinating, Andrew. Thank you so much. And I love all these visuals. This is actually a paper by Dr. Cameron, which was published in Oxford University's MNRAS journal. So feel free to check that out. I'll also include that in the description as well. If you haven't checked out the previous podcast episode, then make sure to do that by clicking here. Make sure to subscribe, like, share, and comment down below. Trust me, I'll respond. Test me.